about detecting offensive language and hate speech with collaboration with Dr. Hind Al Khalifa and Dr. Abdul Mohsen Al Thubaiti. So the details about the shared task can be found in this link. It's divided into 3 subtasks. In subtask A, we want to detect whether the tweet is offensive or not. And in subtask B, whether the tweet has hate speech or not. And in the subtask C, we want to identify the fine-grained hate speech type. And the data and the details of the shared tasks can be in separate links on CodaLab competition platform. Subtask A, B, and C. Why is this topic important? Detecting hate speech and offensive language is very important for applications like content moderation, detecting or predicting the cyberbullying, measuring polarization, propaganda accounts detection and troll, and also detecting hate crimes. We observed, for example, an increase in racism against Asian after Trump uses the term Chinese virus. So detecting hate crimes and hate speech is very important for the safety of the community. So we define the offensive language as any kind of socially unaccepted language, and hate speech is when we use this language against people, like insulting people or attacking people, threatening people, etc., based on common characteristics such as their race, ethnicity, nationality, religion or belief, ideology, disability or disease, social class, gender, etc. So we define fine-grained hate speech types, hate speech 1 to up to 6, and the examples are shown. We use the data set of almost 13,000 tweets collected using emojis that are commonly appear in offensive communications, and we annotated them manually using crowdsourcing platform, Appen, and each tweet was judged by 3 annotators. And finally, we have 35% of the tweets are labeled as offensive, and 11% of the total data set has hate speech, and we have here a number of tweets with different types and examples. We have 40 teams registered in the competition, and 17 teams submitted their test runs. 10 teams submitted their system description papers, and we accepted 8 papers. This is a list of the papers from the accepted teams, and we would like to thanks all the teams that registered, all participated in the shared task. The teams are from aiXplain from US, iCompass from Tunisia, Alexandria University, Helwan University, German University in Cairo, and Meta in the US, and also University in Spain. And all teams participated in the subtask A, but almost half of them participated in tasks B or C. Now the winning teams. Subtask A, the winning team is GUF from Helwan University, Ali Mustafa and colleagues. They achieved the accuracy of 0.86, precision of 0.85, and recall of 0.84. And the official measure was the macro average F1, and they achieved 0.85. Immediately before the Meta AI, normally we use 2 precision in comparing the system results, but before we have many results are close to each other. We use the 3 digits to compare teams. As we can see, very strong competition between GUF and Meta AI, and also AIXplain, and also Alexandria University. Thank you so much for participating, all the teams, and congratulations for the GUF team from Helwan University. For subtask B, detecting whether the tweet has hate speech or not, the winning team is iCompass from Tunisia. They achieved accuracy of 0.94, precision of 869. Meta AI achieved better precision than iCompass, and they achieved the recall of 0.81, 0.80, and the official score macro F1 was 8.3 immediately before Meta AI and Alexandria University. And for subtask C, again, the winning team is iCompass with a strong competition with Meta AI, and the official score is F1 equal 0.528. Thank you so much. Congratulations, and thank you. Now we will listen to these great researchers and know about the details of their research papers. Thank you. Now I stop sharing, and I think all the talks will be removed to Dr. Hind, right?
Exactly, yes. So Ali is there. Ali Mustafa with the paper Proof at Arabic Hatespeech 2022.
So this is the winning team of subtask A.
Yeah, he is presenting first. So Ali, are you there? I see his name, but I'm not sure if he's hearing us. So for the sake of time, let's switch to the next paper until we see Ali responding. Muhammad Aziz.
Yeah.
Assalamu alaikum. Yes, I'm here.
Yes, please. The floor is yours.
Thank you so much. Okay. Is my screen visible?
Yes, but without the slides.
Yeah, okay. Good.
Yes.
Okay. Should I start?
Yes, please go ahead.
Thank you. Okay, so I'd like to start by thanking the OSACT committee for this great workshop. This was actually my first ever competition, and I was so hyped to take part in it. My name is Muhammad Aziz Bensir. I'm an intern at iCompass, and today I have the honor of sharing the details of the project I submitted. The following is the system we ended up submitting. It's basically a multitask model that we built by fine-tuning MARBERT, which is a pre-trained BERT-based model. We fine-tuned it using convolutional neural networks, bidirectional quasi-recurrent neural networks, which are a mix of convolutional and RNN dense layers. And finally, ReLU dense layers. And for the output layer, we ended up making 3 output layers for each task. The first being the sigmoid layer for the offensive binary classification. The second being a softmax classification for all the hate speech category. And the third is another task we added, which is called offensive and not hate speech. As the name suggests, we added this task to detect comments that are offensive but not hateful. This is to make the most out of the inductive learning property of multitask model, and it gave us a 4% increase in hate speech detection. The pre-trained model MARBERT was trained on 128 gigabytes of tweets gathered from multiple dialects. It clearly outperforms all of its competitors. This was also shown in our results, in the results we submitted in the papers, as we also tried MBERT, XMLR, 5T, and ARABERT, but MARBERT clearly had the upper hand when it came to multi-dialect tweets. For the dataset, the initially suggested dataset were very skewed, so we had to augment it using another dataset called Al-Hisab, which stands for Levantine Hate Speech and Abusive. It's a publicly available dataset made by my mentor, Hatem Haddad. And the dataset basically gives 3 labels, which is hate speech, abusive speech, in normal. So we had, for the sake of this workshop, we had to relabel it into all the different hate speech categories. And after adding it to the original dataset, we had to downsample the offensive and normal and oversample the hate speech to make it a little bit more balanced. For the pre-processing, we took a rather simple approach to mimic the way Marbert is used, to mimic the tweets Marbert is used to. We did that by simply removing all the non-Arabic tokens like the user, URL, and LF. We normalized all the hashtags and we removed all the white spaces. The following are a few examples of some tweets from the dataset before and after running through the pre-processing pipeline. These are our results on the dev set. As we can clearly see, the augmentation did pretty well on subtask A and subtask B, but it made subtask C drop, which is actually better because in the previous results, the model was overfitting on the easier classes and it couldn't actually generalize well. And as we can see from our results on the test set, we pretty much scored the same. We pretty much had the same scores that we had on our initial dev set, which is a good sign that the model generalized pretty well. This was my short presentation. Thank you so much for the invite. For more information, you can contact us on the following emails. Thank you so much.
Thank you, Mohammed. So, Engineer Hamdi.
Yes, Dr. Hind.
Yes.
Questions? Yeah, we have questions.
Yeah, go ahead.
Hey,
questions for me?
Yes, this is Wissam. I have one small question. We decided to remove emojis from while pre-processing. Yeah, but from what I remember, I think Marbert had emojis in the vocabulary. So
yes,
any like reason?
Yes. Well, at first, we tried to mimic the same pre-processing Marbert had, but that gave worse results for some reason. So we just tried modifying it a little bit to till the point where we got actually good results. We even tried translating emojis, which actually didn't work. Our only choice was to remove them.
So any question? Thank you, Doctor.
Thank you. Now back to Ali. Ali is here. He's here.
Yeah, I'm here. I'm sorry for that. Okay. Okay, my screen is clear now.
Yes.
Okay, thank you. Assalamu alaikum, hello everyone. My name is Ali Mustafa. I'm today presenting our paper entitled Breaking the Loss Function Convention for Data-Imbalanced Arabic Offensive Text Detection. Now we have our agenda. We will start by motivating our method, talking about essential components in our method, then giving a brief about results, and concluding with future works to future directions with this method. First of all, offensive speech has expanded an unprecedented rate in today's digital age due to spreading a lot of social media platforms and also absence of controlling this process. Actually, it's not offensive speech only. Actually, it's fake news also has expanded. But now offensive detection research in the Arabic language is still in its early stages with with very, very few notable works. This is a problem that most of the Arabic offensive dataset have a long-tailed data distribution, which means that the distribution is very skewed, and there is a data imbalanced problem here, which is if we have now offensive and non-offensive, the offensive clause it's 10% of the overall distribution. So this problem will make some bias towards the non-offensive and will affect the model performance. Most of the researches from a point or from our literature review for offensive detection doesn't focus actually on the data imbalanced issue and doesn't focus about how to overcome it and illustrate a good methods for ADIT. So our methods will talk about this problem. First of all, we made some pre-processing for text, like eliminating non-Arabic letters, punctuation marks, digits, and Arabic diacritics, normalizing some text, like normalizing some characters for characters like al-alif, al-ya. Also make some removal for the elongation case, like because like a goal to goal, wow is a frequent character here in the middle, so we try to eliminate this elongation for like tokenization process will affect by this problem, and the sequence length that maybe increase the runtime. For fourth point, which is replacing URL with a Rabbit. Why did we do that? Because like changing the URL value, like changing the URL value like www.x.com, www.y.com won't be affect the decision of the performance, the decision of the offensive or non-offensive. The same goes for mentions and emails. So we normalize it with some tokens to make the model more precisely about this token. Regarding to the loss function, that is our research focus on it, which is we try to use different loss functions with different settings, with different also valuations. We tried weighted cross-entropy, which is the standard for the deep learning literature or machine learning literature to overcome the problem of data imbalanced. Focal loss, weighted cross-entropy combined with level smoothing, focal loss combined with level smoothing, dice loss, Tversky loss, focal Tversky loss, and finally vector scaling loss, which is recently published in 2021. We applied these loss functions to some pre-trained models. What is the pre-trained models that we used? We used some pre-trained models that is actually pre-trained on the tweets. Why we use it? Why we didn't use it using like pre-trained in Wikipedia? Because following the literature that fine-tuning the models that is pre-trained on Twitter data that is improving, which is improves the fine-tuning performance over the training on standard data like Wikipedia. So the fine-tuning procedure has done it completely on tweets, which is actually pre-trained on tweets. So it will improve the fine-tuning of the process, the fine-tuning process in the fine-tuning. We choose 3 models. Which is our model. We tried another models, which is we will discuss it later. But first model is Qawarib, which is trained on 420 million tweets and 120 million sentences. We tried these models with different loss functions and pick up the best model with the best the model with the loss functions that gave the best performance. So Qawarib was trained with dice loss, achieved 85.7 on F1 score. Second model was Marbert. Marbert was trained on 1 billion Arabic tweets by randomly picking some tweets. Marbert was trained using focal loss plus label smoothing, which achieved F1 score of 85.66. Final model was Marbert version 2. Marbert version 2 is the same as Marbert, but with longer sequence lengths of 512 tokens. As a result, increasing the number of tokens. This model was trained with VS loss, obtained the F1 score 85.21. Here we followed some ensemble learning paradigm. Why we do that? Because like we noticed that the mistakes that made by each model is different from others. So ensambling, making ensemble learning will enhance, maybe will enhance the model ability because taking advantages of each model and discarding these disadvantages maybe improves the model ability, model performance. Results, we tried some different models like Marbert. We tried to excluding the emojis, which is produced 85.7, not a very impressive result. We tried Arbert large Twitter 85.1. We tried Qawarib 85.4. Arbert based Twitter 85.45. Marbert version 2. The best individual model was lighting gradient posting machine with a fine-tuned Qawarib embedding on our dataset, which achieved 85.7. But it's the best model, but individually only. Talking about the best ensemble learning model, which was it like we ensembled light gradient posting machine with Marbert version 2, achieving 86.4. Ensembling Arbert based Twitter, Marbert Qawarib 86.7. The best model was Marbert version 2 plus Marbert and قوارب achieving the best results over the individuals and ensemble learning models, which is 87.0 in the actually all these results on the development set. This is what I'm talking. This is what I stated before, which is we picked the best 3 models: MultiTask, MultiTask version 2, قوارب. We tested it with different loss functions like width cross entropy, width cross entropy smoothing, focal loss smoothing, dice loss, Tversky loss, focal Tversky loss, and VS loss. For MultiTask, the best model was the best loss function was VS loss, achieving 85.6. For MultiTask version 2, the best model was 85.2. For قوارب and for قوارب, it was dice loss, achieving 85.7. Then we ensembled these models with the best loss function for each. The official results states like that GUF achieved the first place with precision 85.6, recall 84.8, and finally micro F1 score 85.2. Second team was Meta AI, achieving F1 score 84.5. I think it's some difference between the first and second team, which may state that our method maybe actually enhances the model performance, and these loss functions actually affect the model performance and achieving an impressive results. Conclusion feature works. In this work, we proposed a method for dealing for Arabic offensive text. We aimed to replacing the standard weighted cross entropy with different loss functions instead of using like standard weighted cross entropy or weighted cross entropy is a standard for any machine learning solution or deep learning solution which have the problem of data imbalanced. But we state here that standard weighted cross entropy, it's not the best loss function in the situation of data imbalanced. There is a lot of loss functions. We try to use different range of loss functions. This loss functions enhances the model macro F1 score by like 0.5 to 2% for different models. For feature works, like we aim to try those loss functions with different tasks, like some tasks of them are machine reading comprehension. Machine reading comprehension actually serves very from data imbalanced problem, because like if this question, if this answer in this context, so this indices is classified as answer and others as not answer. So all of the other words, all of other sentences in some text will be negative. So it will serve from the data imbalanced problem. Actually, this research, if it applied in different tasks, not limited to MRC, to named entity recognition, sentence analysis, will actually assist the researchers in better addressing the problem of highly imbalanced dataset, especially in Arabic literature. We have some appendix here, like we try to model interpretability, like to see if the emoji actually affects the model performance. We see here that the emojis actually affect the model performance. Here, offensive, non-offensive. Non-offensive was red, and it's the degree of colors, green, and its degree of colors or its intensity. As it increases, it states like that this word actually affects the decision with more weight. So like here, offensive word يلعنهم affects the model performance. Here, the angry emoji affects the model performance by offensive. And in the non-offensive case, كلمة word ناجح or زينة.
Okay. We are out of time. Thank you very much. We are waiting for questions from virtual audience or from in-person audience. Thank you.
Thank you. Any questions?
Yes, quick question. This is Wissam again. Okay. My question is about the Arabert Twitter. Did you use the sequence length 128 or what?
The final model in the Hugging Face.
Yeah, because like,
I think it's which is fine-tuned in the tweets or pre-trained extra tweets.
Yep, but when I fine-tuned the model, I only used the 64 sequence lengths before, because Twitter is like very short. So in your fine-tuning, you kept it at 128.
Are you asking about the sequence lengths of the fine-tuning?
Yes. Yes.
I calculated the max length according to the I calculated the sequence length according to the max length of RBERT tokenizer.
Oh, okay, cool, perfect.
Okay, thank you. This answers your question?
There is some question in the chat for Ensemble and learning. Do you just use the models combined at inference time, or they trained jointly?
No, at the inference time, we used a voting mechanism in the inference time only, not trained jointly in the training process.
Perfect. Okay, thank you, Ali. Can you stop
thank
sharing? So we have Angel.
Hola, can you hear me?
Yes, we are.
Okay, I'm going to share my screen. Let's see. No. Can you guys see my screen?
Perfect, yes.
I'm going to start. Hola, hi, my name is Angel Felipe Magnoção de Paula. I'm a first-year PhD candidate at University Polytechnic Valencia in Spain. And today I'm going to share our team solution in order to solve the Arabic Hatespeech 2022 short task. I start highlighting the main points of the competition. First, it was divided into subtasks. Subtask 1 was offensive language detection, where the model have to infer if a text chunk, in this case a tweet in Arabic, is offensive or not offensive. The subtask 2 were hate speech detection, where the model have to infer if the tweet is hate or not hate. And the final, the subtask 3, is the fine-grained hate speech classification, where once we know that Twitter is hateful, we have to classify this type of hate between 6 classes: hate, race, religion, ideology, disability, social class, and gender. Now the main points of the data. The organization of the shared test provide 3 data sets: the training, the development, and the test set. The training development contains tweets plus the labels for the 3 subtasks. And the test have only the tweets, and the results in the test were used to rank in the teams. Counting out the tweets among the 3 data sets, we have 3,000 tweets. And the official metric to ranking the results were the F1 macro. Now I'm going to highlight the main points of our solution. First, we standardize the solution. We use one solution that could be used for the 3 subtasks. So you decide to use language models. And we decide to use 2 kinds of language models: the monolingual language models and the multi-language language models. Among the monolingual language models, we use RBERT, which is Arabic BERT version training Arabic language, RGPT2, Electrica, and Alberto Arabic. All these monolanguage models are transformers pre-trained in Arabic language. Among the multilingual language models, we use MBERT and XLM Roberta, which were trained in more than 100 languages. But among these languages, there was Arabic language. In order to improve our results, we want to aggregate the inference of all these monolanguage models. So we decide to use ensembles, and we use 2 types of ensembles: the majority vote and the high sum. The majority vote select the most predicted class among the class predicted by the language models, and if there is a tie, to randomly select one of the tie classes. And the highest sum aggregates the output value of each language model separately for each class and select the class with have the high sum. Now I am going to walk you through our solution, which has 3 steps. The first is a cross-validation or 5-fold cross-validation, because we want to discover the suitable parameters for each one of the 6 language models to be able to make good inferences. So we use the training data to perform the 5-fold cross-validation, and we are concerned about the learning rates, dropout, and fine-tuning epochs. We were surprised because the dropout and learning rate was the same for all the 6 models. The learning rate was 0.0005 and the dropout was 0.3. On the bottom left, we have the fine-tuning epochs, the suitable fine-tuning epochs for each one of the language models, for each one of the subtasks. So once we knew the suitable parameters for each one of the models, we want to discover the best models for each subtask. We want to discover the two best models for each subtask. Why you want to discover the two? Because the competition only allowed 2 submissions. So we want to make the best submissions. So what we did was, once knowing the parameters, fine-tuning the models in the training data and make prediction on the development data. And once we had the results, we create the ensembles. On the right, we have the table with our top 2 model results on the development data. I can mention about this table that the Hatespeech ensemble was always at the top 2, and it was always followed by a monolingual model. And I will talk more about this in the conclusion of the presentation. Now I'm going to the last step. First, we aggregate the training in the development data and create a bigger data set with more data points. And knowing the suitable parameters, we fine-tune all the models from 0. Yeah, once we have these models trained, we made predictions on the test set. Once we had the predictions, we create the ensemble inferences too. On the bottom left, we have our official results on the test data, plus the baseline of the competition. And as we can see, based on the F1 macro, which was the official metric for the competition, we were way better than the baseline, but not only for the F1 macro, but also for accuracy and precision recall too. Now I'm going to wrap up the presentation, highlighting the 4 main points. First, that the Hatespeech seemed a suitable way to aggregate monolingual models outputs, because we had our best results using this ensemble. The second is that the monolanguage models seem to be well trained, because we have been working with a lot low resource language, and usually or many times the multilingual models after fine-tuning perform better than the monolingual models for this language, but it wasn't the case here using Arabert and the other monolingual transformers pre-trained for Arabic. So well done for this guy who create these models. And I want to highlight again that our results were way better than the baseline. And we compared our results with the last year competition, and we are around top 3. So seems to be a good results this year. We didn't perform so well, but was nice to participate in the presentation. Here are the references that we used to create the presentation and also guide us during the creation of the models and our solution. Here are my contact. First, I want to say thank you for all of you for watching the presentation, and I am open for questions.
Thank you very much. So, any questions from the virtual attendees? So, Engineer Hamdi, maybe from your side?
Questions? No, Dr. Hadi.
Nothing. Okay, so next to the next presenter, who is Badr Al-Khamisi from Meta. Badr, are you there?
Yes, I am here. Can you hear me?
Yes.
Okay.
Can you share your slides now, please?
Yes, I'll share my slides.
Thank you.
One second. Okay, can you see my slides now?
Yes.
Great. Okay, hi everyone. My name is Badr Al-Khamisi. I'm an AI resident at Meta AI. I'm going to present our work, our submission to the Arabic Hatespeech 2022 shared task. And I worked, this work is done by me and Mona Diab. So the agenda for today, I'm going to first present the motivation for the Hatespeech competition, then briefly describe the data set, followed by that the system description and the results, and then an error analysis to see where the model failed and where it succeeded. So the motivation is, first of all, is online harassment. Like studies have shown that 41% of internet users have been harassed online, with a third of these cases being targeted for something related to their inherent identity, such as race or sexual orientation. And when we say inherent identity, that implies that they're being targeted by hate speech. Also, the massive content of shared on social media platforms renders manual filtering of such malicious content impossible, driving platform providers to resort to automated means for detecting hateful content. Therefore, in order to have automated means, we need to have good machine learning systems that detect hate speech. However, hate speech data have been proven to be hard to collect, especially for low resource languages such as Arabic. For example, studies have shown that only 1 to 2% of randomly collected samples of Arabic tweets are abusive, and only a small percentage of these are considered hate speech. Therefore, there is a huge problem of data imbalance, as previous presenters presented. So the data set, I won't go through it, as I believe you all know the data set pretty well. But maybe quickly, these are the number and percentages of tweets as represented in the entire corpus of each annotated category using this work. However, note that the percentages do not add up to 100, since all hate speech tweets are a subset of the offensive ones. And these are some examples for each class of datasets, for each class in the dataset. I'll go through the system description now. So we used the Marbert v2 as our core model, and we framed it as a we framed the three subtasks as a multitask classification problem. Specifically, the input text is encoded using Marbert v2, and it then passed with 3 task-specific classification heads. Each class-specific head is made up of a multi-layered feed-forward neural network with their normalization. And we train them jointly, and we employ something we call self-consistency correction, which I'm going to describe in the next few slides. But note that the final model is an ensemble of several trained models, each of which uses different set of hyperparameters. And to obtain the final prediction, we perform an element-wise multiplication of the corresponding probabilities across the different models, then take the argmax in order to get the final prediction. So the self-consistency correction method was only employed in the fine-grained hate speech classification, which is predicting the hate speech type. And the idea of it is basically we have 3 independent predictions from the three heads. However, like we observe that they're not they have some dependency between them. For example, a hate speech tweet must be an offensive tweet as well. And hate speech classified, if the hate speech type had classified it as non-hate speech, then it must be not hate speech. The hate speech head must present it as a not hate speech class. So we correct the method using what's described here. And we find that this can actually boost the performance of the hate speech classification by almost 2%. So the results. Here's an ablation study where we show that when we train the task, a single task model versus a multitask model, we find that the offensive detection task actually perform better using the single task model. However, multitask helps the hate speech tasks, as they have like more imbalanced data, and here we show in the high speech classification, we show the results before and after self-correction as previously described. This is the test performance compared to the baseline model we presented in Qarib. The reference is below. And we see that the hate speech, our multitask model outperforms Qarib in all the subtasks. Go through the error analysis now. So we analyzed the predictions between each subtask head, and we found that there is a contradiction between some of the classification heads, which actually led to the idea of the self-consistency correction method. So what I mean by contradiction, I mean that the offensive, like just as described, for example, the hate speech detection must be an offensive tweet as well. and so on. And we found that using self-consistency decreases the contradiction considerably, as shown in the Hatespeech classification subtask. And here we report the percentage of false positives and false negatives for the best checkpoint for each subtask. In the Hatespeech classification, we report the percentage also before and after applying the self-consistency correction method. We observe that the self-consistency correction method actually increases the false positives, but this is in the Hatespeech context is actually better because, not better, but like it's like the false negatives is actually more important because that will lead to under enforcement versus over enforcement in the Hatespeech classification tasks. Here are some examples where we show the first row is the predictions, and the second one is the ground truth. We show some examples where the self-consistency correction method actually was able to improve all of those predictions into the correct prediction in the end. And this is all described in detail in our paper. Yeah, and thank you. And please let me know if you have any questions.
Thank you, Badr. So any questions from the audience, in person or in virtual? Engineer Hamdi. Yeah.
Yes. So because the data was annotated using crowdsourcing, and we know there is a limitation for the accuracy that we can expect from crowdsourcing. And also tweets are cover many dialects and not necessary to find annotators on crowdsourcing platforms who understand all the dialects. So typically have some annotation errors. So can we automatically detect some of them better?
Sorry, can you repeat the question? I didn't get it exactly.
Sorry, again?
I didn't get the question. So you're saying, can you repeat the question again?
Can we detect the bad annotation automatically with high accuracy?
The bad annotation? What do you mean by the bad annotation?
The bad annotation, yes. Yes.
And what do you mean by bad annotation? You mean bad annotation from the original data set?
Yes, exactly. Yes. We know that there is some annotation errors in the data, let's say 5%. Can we use some automation to trigger or flag some of them for another round for quality control, let's say?
I mean,
because I think I read your paper and you mentioned something about inconsistency or errors in the data annotation, right?
Yes, that is true.
Yeah.
Actually, I haven't analyzed this, but I think it would be very important to actually interesting to see like if we can automate this using the trained models. But I have to investigate this further in order to confirm.
Thank you, Badr. Any further questions? Or we can switch to the next paper. I think CHILLAX team are not there. No one is presenting from the team. So we are going to the next paper by Ahmed. Ahmed, are you there?
Hello, yes, I'm here.
Yeah, please share your slides.
Okay, 1 second. Okay, can you please give me 1 second because I'm facing some technical difficulties while sharing?
Okay, no worries. Can we go to the next presenter so that you can have more time?
Okay, it will be wonderful if you did that. Thank you.
Nihal, are you there?
Yes, I'm here. Can everyone hear me?
Yes.
Okay.
Can you please share your slides?
Yes, 1 sec. Okay, can everyone see my slides?
Perfect.
Okay, thank you. So my name is Nihal, and I will be presenting my work on behalf of myself and Dr. Mervat Abul Khair. We contribute to subtask A, which entails classifying offensive and non-offensive tweets. We aim to use representations from state-of-the-art pre-trained models in order to classify those tweets. However, a question worthy of asking is, are these representations optimal enough for the task? Now, a research discovered that neural-based models during pre-training, they tend to favor high-frequency words over low-frequency words. So this distorts the shape of the embedding space, and the embedding space becomes composed of sort of two clusters, almost two clusters, one containing high-frequency words and one containing low-frequency words. Now, we wouldn't be so hinged on the idea of how the embedding space looks like, or are the representations expressive enough or not. But when we looked at what the high frequency words were in our data set, they were basically just stop words. But when we looked at the low frequency words in our data set, they were the words we wanted to emphasize the most in our representations. So this is why enhancing the representations in our system is a major step in our overall system. Now, I refer to this in my paper as isotropy. Within the context of embedding spaces, isotropy is essentially a description of how an embedding space looks like. If an embedding space has its representations scattered around the origin homogeneously, then we call this an isotropic embedding space. However, if an embedding space is the opposite of this, we get what we see here in this figure. In this figure, we try to project the dominant directions of our data set. If we inspect the colors of the representations, the darker the color gets, the more frequent the low frequency words are. So basically, the lighter colors are the high frequency words, and they are closer to the origin, but the low frequency words that are far away, and the embedding space is taking the shape of a cone, which is a trait of embedding spaces that suffer from the representation degeneration problem. Now, our overall system consists of extracting representations from Marbert. We chose Marbert in order to stay at the same domain, since Marbert is pre-trained on tweets. Then we try to make these representations, and we enhance them using a method called the cluster-based approach. And then we pass those enhanced representation into bidirectional LSTM. Now, there have been several methods proposed in order to enhance the quality of representations and make them more isotropic for static and contextual representations. But the central or the main idea was to remove the dominant directions. The dominant directions are essentially the high frequency words that we do not really care for. So our method of choice is the cluster-based approach. It was created by Sara Rajai. So in the cluster-based approach, we, as the name suggests, we cluster our representations into a certain number of clusters using k-means. And for each cluster, we employ 3 steps. We make them zero mean, and then we compute the dominant direction of each cluster. And then we remove a specified number of dominant directions within each cluster. Now, we chose to create 10 clusters from our data and remove the top 8 directions. The results after passing these enhanced representation to our bidirectional LSTM for the development data set is 81.2% for the accuracy and 79.1% for the F1. And our test scores are 76.5% and 74.5% for the accuracy and F1 respectively. When we tried to look at what the model managed to classify and misclassify, we found that the offensive samples that were correctly detected were 766 out of 898, that is on the def set, and 271 out of 368 from the non-offensive samples. which is basically 14% misclassified non-offensive tweets, but the model misclassifies a larger percentage of offensive tweets, and we attribute this difference to the bias in the train set. Now, we tried to employ different settings to our model. During making the representations better, we tried to cluster using different number of clusters. We tried 10 clusters and twin clusters, but we found out that results are very, very similar. So we reckon that maybe we have removed directions more than we should have. So basically, we should have removed a lower number of directions. Thank you. Questions?
Thank you, Nihal. Any questions from the audience? Seems there is no questions from the virtual audience.
Thank you.
Here, Hamdi. I think they don't also have questions. Thank you, Nihal, again. Let's switch now to Ahmed. Are you there, Ahmed?
Yes, I'm here.
Please.
Can you hear me good?
Yes.
Okay, 1 second. You can see the presentation, right?
Yes.
Okay. Good evening, everyone. It's Ahmed Shapiro from Alexandria University, Faculty of Engineering, Computer and Systems Department. This work is co-authored by Dr. Ayman Khalafallah and Dr. Marwan Turki. Actually, I'm a senior undergraduate engineering student. We can go directly to our EDA approach. We first did EDA on the data. We found two things, that the data was really imbalanced. It's sorted in the presentation from highest to lowest.
Sorry, Ahmed, sorry for interruption. Ahmed, sorry, can you please raise your voice or make the noise a little bit less?
Okay, 1 second, give me 1 second. I will try to put a headset or something. Hello, can you hear me good now?
Okay.
Hello?
Yes.
Okay, maybe.
Without mics, the microphone is better.
Go ahead, Ahmed.
Hello?
Yes, Ahmed, go ahead.
Okay, give me 1 second. I'm really sorry for this. Okay. We found that the hugest imbalance were in subtask C, followed by B and A. Actually, we found another thing, that only 2 examples out of the whole data set, including the training and the dev data set, did not have any emojis, which means that approximately 100% of the data examples had emojis in it, which were a reason when we selected our encoder, which we will discuss next. We decided to follow a transformer-based architecture, pre-trained on Arabic transformers, which is followed by a classification layer. But the drawback of this approach is that it's overfitting in a small-scale training data set, and also it overfits when there is a class imbalance within this data set. For the encoder selection, we had actually 2 models in mind, ARABERT and MARBERT version 1 and 2. For ARABERT, its training data was mostly in MSA. There were no emojis in the data set. It was removed at a pre-processing step. They used FRASA segmentation also in pre-processing. Actually, we decided to select this model because, as mentioned in our related work section in the paper, it was the top performer in the multitask learning. The second model was MARBERT. Its training data set with 100 billion tweets. Actually, the main reason we selected MARBERT is because it's similar to the data distribution we have in with respect to the length and the dialects, they are all tweaks, okay? And especially because it had an emojis in its embedding layers, which means that it understands the meaning of an emoji. We found two versions of MultiTask, version 1 and 2. The only difference is that version 2 used more data and trained for 40 epochs. For the selection, first of all, we did a classification fine-tuning using Hugging Face on the 3 models. Without any pre-processing, we found that we found that both versions of MultiTask outperformed RBERT. So we decided to eliminate RBERT from the rest of the experiment. Okay, for our pre-processing, first of all, we did a normalization of Arabic letters. The alif with the hamza is removed, and so on. We did a normalization of punctuations and digits. We did hashtag segmentation, and we removed the diacritics except shadda, because actually it will differ in the meaning of the word with and without shadda. The symbols or non-Arabic symbols, and repeated characters or emojis more than twice. Actually, we decided to remove repeated characters more than twice because most of the words in the Arabic does not repeat a character more than twice. So we eliminated elongation by doing this. And for emojis, after EDA, we found that actually the emoji most of the time, it's not always has a direct meaning with the semantics of the tweet. Actually, I may be sarcastic and post something I'm really happy about and post some angry face with it. So we eliminated emojis repeated more than twice to eliminate the bias and the scarcity in the representation. After we did that, we tested the MultiTask version 1 and MultiTask version 2. We found that our pre-processing approach improved the results in both versions, but the MultiTask version 2 outperformed the MultiTask version 1. So we decided to move forward with MultiTask version 2 and our pre-processing step as our feature extractor for the rest of the experiments. The approaches, actually, our goal was to explore different approaches than classification fine-tuning. To explore these approaches more than more than doing any numbers, okay? For the first, we did a classification fine-tuning. It's an encoder and single classification head. The objective is to take a decision. The encoder is fine-tuned end-to-end with the classification head. For the contrastive learning, the goal is very different from the classification. Its goal is to differentiate rather than classify, to differentiate between the two classes rather than saying which is which, okay? And it had a huge advantage in class imbalance, as we will discuss later. It provided an m times n data. We will discuss those number later, and the multiple variant of losses. Three type of losses: the contrastive, which calculate the loss for all the examples; that the online contrastive, which only calculate the loss for the positives that are far apart and the negatives that are really close; and the batch all triplets, which is a triplet loss that calculate the loss for all valid triplets within a batch. In contrast to the classification fine-tuning, the contrastive learning is done in 2 steps. First of all is fine-tuning the encoder on a contrastive objective, then freezing the encoder and training the classification head after that. For the multitask learning, it provides an inductive transfer between tasks. Actually, I won't go through this because actually a previous presentation went through multitask learning. Also, its advantage, it somehow eliminates data imbalance because the task can learn from each other. Its drawbacks is the difference between data set distributions. 1 second. The difference between the data set distribution, actually, the most of the work we saw while researching these problems, they use a data set from a different tasks, okay? So it may be was collected by a different way, and we noted that in our result the progress was not consistent in all subtasks. Okay. The data construction for the contrastive learning, we have m offensive examples and n offensive examples. We create 3 pools of data points. two positive pools and one negative pool. The first positive pool is from offensive and offensive, which result in M squared data samples, and the second positive pool is from the non-offensive and non-offensive, which result in N squared data samples, and the third negative pool is from offensive and non-offensive, which result in M of N. Okay, which brings us that we have a maximum size of data, which is M squared plus N squared that plus M times N. The samples are balanced across the positive and the negative pools. We just say like we need 100K of examples. We sample 50K from the negative pool, and we sample 25K each from two positive pools. And for the multitask learning, we had two versions of the data: the non-balanced one, which is the data associated with the task, and the balanced version. The balanced version is a concatenating of OSACT2022 and OSACT2020 for subtask A and B, and offensive L for subtask A only, and then undersampling the majority class of the data. The result and discussion. For subtask A, actually we tried everything we did in subtask A, from classification, fine-tuning, contrastive, and multitask learning. We can see that online contrastive with 50K examples outperformed online contrastive with 1 million examples. Actually, the result may not be that significant, but it's still outperforming it. And we can see that the multitask learning with both original dataset and the balanced dataset was not comparable to the results of both classification, fine-tuning, and online contrastive. And we can also see that as the contrastive data increase, the performance degrades. This also may be attributed to the as the contrastive data increase, the performance degrades because this we may need a careful selection, as we mentioned earlier that we have M times N, okay, and the difference in the distribution will degrade the multitask results because of the different ways of data collection. For subtask A, where we delivered an ensemble of our best 5 performers, which is the classification and the both online contrastive trained with 50K and 1 million, and the contrastive with 50K, and the batch all triplet. We did 2 techniques to ensemble both models. Actually, the first one, with the simplest, is it was just we sum the positive and the negative logits and take the maximum, which will be our decision. The second one, it's somehow a weighted voting, which we take the positive and the negative logits as a feature to a logistic regression or any other classification algorithm to solve for the weight for each model. Actually, both performed in a similar way, so we decided to move forward with the former one. This is the class separation. We can see the class separation for Marbert without any fine tuning on the left, on the top left.
Please.
Okay.
Yeah, go ahead. So you have one.
Okay, we can see the class separation between both models that trained with different strategies. Okay, here this so. For subtask B and C, we decided to deliver the model trained with multitask learning. Actually, we noted that training for extra epochs improved the subtask C, but degrades A and B. It can be attributed that subtask C had the highest data imbalance, so it benefits from training more rather than subtask A and B. Actually, also we noted that the data balancing does not guarantee any better results, which can be attributed to a difference in distribution between the data used in constructing the balanced data set. Actually, we move forward with the model trained on balanced data because it achieved a better significant result on subtask B only, as we can see in the table in the presentation. Thank you. Any questions?
Thank you, Ahmed.
Okay.
So any questions from the audience? We have almost 28 participants from the virtual audience, but no one is trying to ask. So back to you, Engineer Hamdi. I think we also don't have any questions from the in-person.
Dr. Hind, do you hear us?
Yes, now, yeah.
You hear the microphone?
I'm asking if you have any questions from your side.
1 second, Dr. Hind. 1 second, Dr. Hind. But we have a problem. Dr. Hind, can you please move? 1 second, Dr. Hind.
Sorry, Engineer Hamdi, are you
Yeah,
talking
hello.
to me?
Can you hear me now?
Yes.
Yeah, okay. This is Jack Halpern from Japan. We are building a very large scale full-form lexicon for Arabic. And I want to ask a question about the normalization. We have to do a lot of normalization to detect orthographic variations and so on. So you said that you don't eliminate the shadda, but you eliminate the hamza. I would like to understand the details because this makes a huge difference in the recall and in the extraction. So when you eliminate hamza, I'm sure you don't eliminate the hamza from the ya and the waw. I suppose only from the alif, right? But if you eliminate the shadda, a lot of the Arabic is just not written with the shadda. So can you give me a little bit of more details on how you do the normalization?
Okay, can you hear me now? Hello?
Yes, we hear you.
Did you hear my question?
Okay, we eliminate the shadda from alifs, okay, from the alif letter. I'm sorry, we eliminate the hamza from the alif letter. We keep the shadda because there may be a different words which is written at the same, okay, but the meaning will differ with the shadda or without shadda. It will not be the same meaning. Actually, I cannot recall an example at the moment, but we faced this. In the data set, and actually in the paper we cited some work that also eliminate the shadda and they gain a better results. And we tried with and without our pre-processing steps and showed that our pre-processing steps were really outperforming the one without pre-processing steps. We should have done an ablation study for each step actually, but this is for future work.
Okay, thank you. It's more complicated than that, but it's okay. Thank you.
Thank you, Ahmed. So let's.
One more question.
Yes. Yeah.
It's
question, please. Yeah.
It's Wissam. I have a question about the shadda again. So when you decided to keep the shadda, I think it's actually doing worse with the model because if I'm not wrong, the shadda is not present in the Marbert vocabulary. And not, I think all bird vocabularies till now, except Arabic bird. I think I verified that. They don't have shadda because we all removed all types of diacritics from all models. So when you actually added diacritics, I think what happens in tokenization step, the tokenizer is splitting the word at least into two like sequences, and you're getting an unknown character in the middle, if I'm not mistaken. So maybe the other part of your pre-processing did better, but this one I don't think that this small thing maybe did worse. That's it.
Okay, thank you so much for your question. Actually, I didn't know that Marbert did not have the shadda, and we can do this also in a future work to try an ablation study of our pre-processing steps. Thank you.
So we normally prefer to remove all diacritics because even with the shadda and tanween, because sometimes the word يحكم, let's say, can be written with shadda and without shadda, and it's confused. Yes, it's confused. يحكم and يحكم, they are ambiguous.
Exactly,
and,
what I'm saying. Actually,
in all cases, we prefer to remove all diacritics, including shadda and tanween. And
okay,
we agree on this.
Thank you.
Thank you so much.
Yeah, of course, yeah, different, but not the hamza on top of wow or yeah, different. Thank you, Dr. Henry.
So
thank you.
So last but not least, Thiago from Explain, are you there? Can you stop Ahmed sharing your screen so Thiago can share his screen?
Hello, everyone.
Hi, yeah.
Yeah, let me try to share my screen. Okay, could you all see my screen?
Perfect.
Yeah, great. Okay, thanks for having me. I'm Thiago. I work at AiXplain, and we did this work also in collaboration with other researchers in AiXplain, Salah, Lucas Pavanelli, and Mohammed. We will present a semi-supervised approach to detect offensive tweets. Okay, So just to highlight, I think this is important. We share what motivates us. It's the same motivation, I think, from the organizers. It's important to highlight that abusive speech on online platforms can cause detrimental effects on users' mental health, especially on the youngest. And any activity, any procedure being manually or automatic to diminish this kind of activity, it's very welcome. So that's why we decided to participate on this shared task. Okay. We just participate on subtask A to actually detect offensive speech. And we saw the first thing that we saw is the size of the corpus. So it was provided around 12,000 annotated tweets. From those, 35% were offensive. So there is a kind of like imbalance. So this is the first thing we noticed, and we did some research to try to balance this corpus, and you will see like the decisions that we took. So first thing that we did some data pre-processing. So in terms of texts, we removed the diacritics and also the tat wheel. And we also did pre-processing on the emojis. So first thing that we did was to describe the emojis on plain English instead of using the codes. And then from English, we translate to Arabic using this machine translation model from 2018. Then we try several features and models in the development, training on training data and testing on development. So in terms of features, we use all kinds of like generations of continuous representations. We did word level and character level TF-IDF. We did one hot encoder of the emojis. We also did a bag of words that we call emoji score. Actually, for each emoji that appears on the text, we measure the ratio, like the number of tweets on the training data, positive tweets on the training data divided by the number of negative tweets on the training data that this emoji appears. We try first generation of word embeddings, this one from 2019, so the CBO, 250 million words. So in terms given a tweet, we find the words, the word embeddings, and we average them, like, and this is the representation of our tweet. And we also test the multilingual universal sentence encoder by Google from 2020. So using these features, we built like a logistic regression on top, and we try to predict whether a tweet was offensive or not. And finally, we tested also the BERT large from AutoBERT version 2, pre-trained on Twitter. Okay, so this is our preliminary results. So here we have all the models like tested separately and also the ensemble of the models. So separately, we saw that the best feature was the character level TF-IDF. Ensemble the character level TF-IDF with other features like word level, muse, and emoji lead to the second highest F1 score on the development set. But this is way lower than the state-of-the-art AutoBERT. Okay, so AutoBERT by itself, only fine-tuning on the training data led to the best results on the development set. So taking this into account, like our official approach that we choose and we want to improve was the AutoBERT pre-trained on Twitter. So here's the trick that we did to try to overcome the problem of the unbalanced data. So we did some data augmentation, kind of like a semi-supervised approach. So we use as the labeler the fine-tuned AutoBERT on the training data. And then we extract a large number of tweets and we label them automatically and take into account the ones that has confidence score greater than 98%. So we use two strategies. And the first one, we extract recent tweets that were published from Qatar and Saudi Arabia. And then like we collected like 200,000, like a really large number, and then we labeled them and we managed to come up with like an additional corpus with around 6,000 offensive and non-offensive tweets. And we use also a strategy 2 that we got also a large database of Arabic tweets. And we separate tweets that has very characteristic words in offensive tweets in the training set and non-offensive tweets. So we separate this sample and then we label them. And again, we got like a balanced collection of around 10,000 of automatic label tweets. Okay, so more or less 5,000 offensive, 5,000 non-offensive. So here we have like our official submissions. The first one was the fine-tune ARA-BERT on the training set and the strategy 1 set, like with the recent tweets that we collected, published on Saudi Arabia and Qatar. And the second submission is also a fine-tune ARA-BERT with the training set, is strategy 1, but also strategy 2, okay? And as you could saw, like in the overview of the share task, this is our results. For the first submission, we got an F1 score of like 84.3. And using strategy 2, augmenting a little bit more the data, we managed to get like an F1 score of 84.9. So we think there is still room for improvement as you can keep collecting data, annotating, and keep running this like iterations of semi-supervising classification. And then, well, just some conclusions that we took from the study that we did. Actually, ARA-BERT, pre-trained on Twitter, seems to be the best model for this task of like detecting offensive language in Arabic tweets. And we also saw that like a semi-supervised approach, augmenting the collection of labeled tweets, so increasing the training data can boost the results.